So we have progressed from chapter 9, which studies simple harmonic motion, to chapter 10, which studies mechanical waves. So for this video, we are going to focus on one type of mechanical wave, which is progressive wave, in which the wave will travel across the medium. So we'll be looking at how does a progressive wave looks like, and what are the parameters that we can use to describe a progressive wave, and from there we see what will happen if we change the parameters of the progressive wave. So this will be how a mechanical wave looks like. But to know whether it's a progressive wave or a stationary wave, we have to let time pass. Then we have to see how does the wave move. So in this case, if I let this animation runs, you can see that this wave here is now moving towards the right. It is traveling to the right. So in this case, we are saying that this wave is progressing to the right. Therefore, this is a progressive wave. Okay, so if the wave doesn't travel to the left, doesn't travel to the right, it remains at its own position, then that one will be stationary wave. But for now, our focus will be on progressive wave. So we can describe the progressive wave using equation. And the equation that we can use to describe the displacement of a progressive wave is this equation over here. So if you have this equation here, then you have your value for A, omega, and K substituted in, and phi as well. If you substituted in the parameters, the amplitude, the angular frequency, the wave number, and the phi and the phase constant, you have a complete equation in which you are able to know how does the wave looks like at any moment in time, at any position along the wave. So this is the equation that we can use to describe how does the displacement looks like at different position of the wave at different moment in time. Okay, so there are a few parameters that are in this equation over here. Over here you can see 1, 2, 3, 4. So let's go through each and one of the parameters to see what do they control. So the first parameter here is amplitude. Amplitude is similar to what you have learned in chapter 9 on simple harmonic motion. It is the magnitude of the maximum displacement that can be achieved here. So over here you can think of x here as a series of particles. You can think of it as every single position there is one particle. Okay, so at each different position x, the particle undergo different amount of displacement. Let's say if I'm looking at this point where my laser pointer is pointing right now, at this position the particle has already displaced by this much in the negative direction, whereas in this at this position, the particle has already displaced by an amount of distance this much in the positive direction. So you can think of this x-axis here as a series of particles, and each of the particles has been displaced by a different amount, either in the positive or negative direction. And the maximum displacement that can be achieved by these particles here, we call it amplitude. Okay, it's the magnitude of maximum displacement. So next, the next parameter will be on angular frequency. Angular frequency you learned about it in chapter 9 on simple harmonic motion, in which it controls how fast is your oscillation. If it's an oscillation that is very rapid, then we call it a high angular frequency. If it's a slow oscillation, then it's an oscillation with low angular frequency. So the idea is similar now in this progressive wave. If you see a wave that progresses very fast, it has a high angular frequency. If you have a wave that progresses very slow, then it's a progressive wave with low angular frequency. So we know that this parameter here, this omega here, it's a parameter that is related to time. Why do we call it related to time? Because we know from chapter 9 that omega here can be related to the period and the frequency. Angular frequency is connected to period, connected to angular frequency by these formulas that we have here. So you can do a bit of recall from chapter 9. So one thing that we can measure most directly from this kind of wave here is the period. It is much easier to measure period. Then from there we calculate the angular frequency and the frequency. So how do we measure the period here? Well, if you just look at this wave over here, you can't determine the period. the period, it's not similar to chapter 9. Chapter 9, you obtain the period by taking the time taken to complete one oscillation. But be careful here, this is x-axis, this is not time axis. If it's time axis, then the time taken to complete one oscillation will be the what you have taking here minus here, then you get period. But this is x, so this is distance, this is in meter. So if you take a measurement from here minus here, you get a distance measurement, not a time measurement. So you can't obtain period just by looking at this graph over here. And actually, if you want to actually determine the period of this graph over here, what you can do is you should let this wave here move. You should let this wave, I've animated this graph actually. So you let this wave move, then you see how much time does it take for this wave to progress by one wavelength. So if this graph is shifted by one wavelength, how much time does it take? You can call it as how much time does it take to complete one wave cycle, or how much time does it take for the wave to progress by one complete cycle, or how much time does it take for the wave to progress by one wavelength. So let's try and determine it. Okay, I will try to let you know when to start the timer, when to stop the timer. Then the interval will be the period. So let's look at it. So if we keep track of this point over here, so this is one wave cycle. We want to achieve one wave, move by one wave cycle. So let's keep track of this point. So let's start. So we start the timer. The time is running. Then we see this wave is progressing. We want one wave cycle. So it's almost there. We want to reach here. Then we stop. So stop. So now if we start, we stop, then we take the amount of time that has passed in between the start and stop. That time will be equivalent to the period. It's the time taken to progress by one wavelength or one complete wave cycle. Okay, so these are the parameters that are related to time. And in this equation, the time parameter is represented by the angular frequency. Okay, so in your chapter 9 SHM, you have your amplitude, you have your angular frequency, and you also have the phase constant. But in chapter 9, we already explicitly mentioned that phase constant is technically out of your syllabus. But phase constant is there if your particle does not start from the equilibrium or does not start from the maximum displacement, either positive or negative. If it doesn't start from this equilibrium position, maximum positive displacement or maximum negative displacement, if it does not start from these 3 points, then we have to introduce a phase constant. Why do we need to introduce a phase constant? Because a sine graph or a cos graph always start from the equilibrium position or the maximum displacement. So if it doesn't start from these 2 points, these 2 or 3 points, what we do is we need to shift the graph a little bit to the left or shift the graph a little bit to the right. And that's where we use the phase constant. Just a little bit of reminder, if you want to shift the graph to the right, then you need to have negative phi. If you want to shift the graph to the left, then you have to have positive phi. So this one you can recall it from a chapter 9 video. Okay, so this one in chapter 10, all of our mechanical wave, right, will have our x equals to 0 start from the equilibrium. Okay, if it's not equilibrium, also it will be at the maximum displacement. It won't start at somewhere in the middle. So definitely you will not see any phase constant in chapter 10. Okay, when you're plotting graph, later you see there's something related to phase constant. But this kind of third term inside the bracket, right, this third term over here will not exist in your syllabus for now. You only have 2 terms inside your bracket. One that is related to time, another one is related to space. So let's get over to the next one. The last parameter in this equation here is k, and k here is wave number. So I say k here is related to, it's a parameter that is related to space. So let's try to investigate it. So parameter related to space basically means parameter that are related to length or distance. Okay, the one that we have encountered earlier is the amplitude. Amplitude is related to how much you have been displaced in a positive or negative direction. So it's the vibration of the particles either vibrating in the positive direction or negative direction. That one is amplitude. But for k over here, k is also related to space, but it determines how wide is your wave or how narrow, how packed is your wave. That one is determined by your wave number. So wave number here is related to something that you have learned from SPM, which is your wavelength. So wavelength is represented by a symbol lambda, and it is the distance between two successive points that are in phase. So let's say so the definition for wave number, you can get it by taking 2 pi divided by the wavelength. So to give an example, a wavelength should be from here to here. So you take one point, then you find the successive point, the next point which is having the same phase as the point that we take. So if you take the distance between that 2 points, the distance will be our wavelength. You can choose to take from one crest to the next crest, one trough to the next trough, or you can take any point to the next point that has the same phase with the point that we take. Okay, no matter what you measure distance, you get the wavelength. So if you get your wavelength, you take 2 pi divided by the wavelength that you determine, then you get wave number. And this wave number is what's representing space in our equation over here. So there are 4 parameters that controls our equation, and there are 3 variables over here. So we have y, which is representing how much you have displaced from the equilibrium position y equals to 0. T here is how much time has passed. So if t is equals to 5, so it means 5 seconds after the wave, 5 seconds after t equals to 0. If it's x, that means if you sub in x, that means we are looking at which specific position of the wave you are interested in. Let's say you are interested with this particular point, the particles that is over here at x equals to 2. Then you substitute x equals to 2 to focus on this particle over here. But I won't go too deep about this because later you see how I apply the equation, how I do my substitution later. Okay, so the next thing I'm going to talk about is this thing over here, this plus minus kx. Plus minus kx here, actually, it dictates how our wave will propagate or how our wave will move. So plus and minus sign in front of the k decides whether this wave will be progressing to the left or progressing to the right. So how we determine the sign, it's like this. We follow this rule over here. So if your motion of the wave is in the negative x direction, or if your wave is traveling to the left, then you use positive kx. It's slightly different from how we usually think about things. Usually we say positive is to the right, negative is to the left, right? But when we talk about positive or negative kx, positive kx means moving to the left or moving to the negative x direction. Negative kx means moving to the positive x direction, which is usually to the right. So this is how we can see whether the graph is moving to the left or to the right based on the sign over here. So in this case, if we focus on this graph over here, this graph here is moving to the right. You can see this graph is progressing to the right. So progressing to the right is positive x direction. Therefore, you should expect your equation should have a negative sign over here. Okay, so this is a general equation. But if you're looking at this specific situation, then you have to change this to a negative because your graph is moving towards the right, which is the positive direction. Okay, so this is the equation. These are the 4 parameters. These are the 3 variables, y, t, and x. And the positive and negative sign in front of k decides how the graph will be moving, either to the positive x direction or the negative x direction. Okay, so that's about the equation. Next, we see how will the wave change if we manipulate these parameters over here. First thing is, if we manipulate the A, let's say if we increase the amplitude, what will happen to the wave is the wave will become taller because you have greater amplitude. That means you have a greater amount of displacement that you can achieve. So if a wave initially looks like this, if you increase the amplitude, then you get a taller wave like this. So how about if you manipulate the wave number? If you manipulate the wave number by increasing the wave number, by looking at this equation over here, you know that if k increase, the wavelength will decrease. So if the wavelength will decrease, that means initially if a wave is this wide, if you decrease the wavelength, then the wavelength will be shorter. So your wave will be more packed right now. So your wave become more packed. Therefore, initially, if your wave looks like this, once you increase the k, you increase the wave number, you will decrease the wavelength, therefore causing your wave to become more packed, something like this. The wavelength is now shorter. Okay, next, if we change the angular frequency by increasing the angular frequency, then we know that angular frequency here, if we increase, then it means you have smaller period. Smaller periods means by you take less time to complete one wave cycle. So if previously one wave cycle takes this much time, then now if you take less time, then you probably see the wave cycle progress faster. Therefore, you should observe the wave to be progressing faster if the omega increase. Okay, we are keeping the k constant. If we increase the omega, then what will happen is initially the wave progress in this kind of speed. But if we increase the omega, then what we'll see is the wave progress faster. Okay, so these are the effects if you change the amplitude, change the wave number, and change the angular frequency. And that's all that that's all that I want to discuss about the displacement equation for a progressive wave.